Hello everyone, welcome to my talk. This talk is about some ideas I explored for the goal of making mobile Linux, especially on the PinePhone Pro, more secure. Many of those ideas presented in this talk will also apply to desktop Linux, and some of that will also apply to embedded devices. This work is sponsored by Linux Australia. They provided me all the devices I need for this work as part of the grant. Yeah. And be mindful that this is not suitable for production due to hardware limitation, but I think there will still be interesting ideas you might be able to apply on the system. And a recurring theme of this talk is security by isolation. In a personal computer, we can defend ourselves against threat of compromising and increase security assurance by isolating security-sensitive data and operation in a dedicated container. And by doing so, we can reduce the attack surface. This talk will be divided into 4 sections, basically. The first one is about increased security assurance with Opti, which is an open source, free, and auditable operating system for the security enclave. And once that is working and we have a working TPM running firmware in the trust zone, what we can do with it, some of the integrations. And then I will also mention about virtualization-based security for desktop and mobile applications to further enhance overall security. And then some of the pathways we might be able to explore in future. So what is security enclave? Essentially, it is a computer within your computer. It is isolated from your primary operating system, which in this case is Linux. And it has reduced attack surface due to smaller code footprint. And it is generally being audited more intensively than your normal Linux kernel or Linux software. It is used to protect sensitive operations and data, and you are probably using it. If you have an Android phone, it's likely running Google's trusty T operating system in the security enclave, and if you are using iOS device, there it's probably running SAP OS. So for things like payment processing and verification, those are also probably done in security enclave nowadays. If you, for example, make a PayPass payment on your iPhone, then that payment verification is done on security enclave. Things like, for example, unlocking your screen with your fingerprint or facial recognition, that is also done in security enclave. And with secure media pipeline support, it's also possible to handle media encryption and decryption on security enclave. Yeah, those are some existing implementations. Those are the most commonly used ones. For Trusty running alongside with Android, it's based on a thing called Little Kernel. And for SAP OS, which runs alongside iOS, it's based on a custom version of L4 microkernel. I'm not quite sure if that's open sourced, but Trusty for Android, that is open sourced. So let's talk about Opti. Opti is another open source security enclave operating system. It mainly relies on more than ARM processors trust zone feature for secure isolation, but the core design of this operating system is portable and is architecture independent. You can port it to, for example, RISC-V or other custom architecture. It provides a platform for trusted applications to run. Trusted applications are applications to perform a specific functionality, things like, for example, on a mobile devices with payment features, that payment would be processed by a trusted application running within the trusted execution environment. And it also provides some common functionalities for applications to take advantage of, for example, secure and persistent storage. With Opti, you can choose to store those sensitive data in an authenticated and protected area of your eMMC called Replay Protected Memory Bank. Memory blocks. So how does it actually work? This is the structure of a common ARM 8 cores running both security enclave and your normal operating system, Android or Linux. On the non-secure world side, you have your, for example, desktop environment, browsers, email clients at exception level 1, which is user mode. You can think of exception levels on ARM processors as different ring levels on x86 processors. They separate the processor into different privilege level. And on the exception level 2, you have the kernel mode, which normally run Linux or probably a pitched-up Linux kernel. And our opt driver is also running inside this level, inside Linux kernel. And for exception level 3, we have the hypervisor mode, which is often not used if you are not running virtual machines on your ARM processor. If you are running things like you are using KVM, then this will be the exception level your hypervisor running under. And there's additional exception level 4, which is called secure monitor level. This is a secure hypervisor that relays data and operations from your secure world and the non-secure world. On the secure world trusted execution environment side, you have your secure enclave operating system, in our case OPT, and you have different trusted applications running on top of it. In our case, there is fTPM, a firmware trusted platform module running on the OPT kernel. And there's a firewall which isolates systems and hardware resources between the normal world and the secure world. For example, there would be regions of memory dedicated to the secure world, which is not supposed to be accessed from the normal world. And if there is certain operation that needs to be done by Linux kernel, for example, accessing eMMC, then this is done via the SMC calls, which relays operation from the T kernel to the Linux kernel, and then the Linux driver will handle the hardware interactions. So then go back to the PinePhone Pro, how does it all integrate together? Well, first, when you power up your PinePhone Pro, it first initializes SOC, which in our case is RK6399 made by Rockchip. When the SOC first powers itself up, it will load code from its boot ROM. That part is fused into silicon, cannot be changed, cannot be audited. It's not open source, it's proprietary. We do not know if it's safe, probably not. And then it loads up two parts of U-boot, the TPL and SPL. Their goal is to initialize SRAM and load other part and load the U-boot proper. And then you have U-boot proper, which loads things like ARM trusted firmwares and the OPT operating system, as well as other things U-boot needs to run, for example, the device tree blob. And then finally, U-boot loads up Linux kernel, Ethereum FS, and other things for a full operating system. Okay, so now we have OPTs running on the PinePhone Pro. What can we do? Oh, first, since we have a firmware TPM, we can do measured boot. At least we can do it partially. And we can have hardware-backed identities and tokens. For example, we can emulate a USB video token backed by fTPM to log in to different service providers, things like GitHub, Gmail, and GitLab. We can also use OPT or rather fTPM to have SSH identity, which is non-exportable. And then we can also do integrity check via one-time time-based password. For example, you can seal a seed into OPT, and then when your system boot up, it will give you a one-time passcode. You can check that against a known good system. And if that password matches, you know that your system is able to, your OPT is working properly, and your system has a level of assurance that you're comfortable with. There are more integrations we can do in future, things like GNU-PG or K-Wallet, to make those things more unexportable. A bit more on firmware TPM. So firmware TPM is essentially a trusted application developed by Microsoft. It runs under the OPT kernel, and it exposes itself to Linux kernel or U-boot as a regular TPM devices. For applications that relies on TPM, you don't have to make any change to those applications. Those should just work. And for non-violate storage, it is backed by OPT secure storage support, which then is backed by eMMC. It's released under MIT. However, ideally, we should have secure boot working with Rockchip RK6399, but in reality, this is not happening because we do not have a working hardware root of trust, and so there is no secure boot. In a perfect world, we should be able to fuse our public key into the chip itself and let the chip's boot ROM to then validate each stage of the payload it's going to load. But we do not have that too, and that is probably under NDA. I haven't figured out how to do that, but if you have RK6399 and don't mind if you burn it, please give that a go. And unfortunately, lower level things like firmware, untrusted firmware TFA cannot be measured yet. This is not really a hardware limitation. It's just I haven't figured out how to actually handle this part of measurement within the firmware. It should be possible, but there are still plenty of obstacles to overcome. Hopefully, those problems can be solved in future revisions of PinePhone Pro. So for measured boot, it is performed by U-boot. When U-boot first boot up, it will measure all the payloads required to boot Linux and store the measurements into fTPM. And then those measurements can later be used from the user land. For example, you can let InsureMFS automatically unlock your root device if all the conditions match. So here is a demo for access measurements from Linux userland. I have to resort in a recorded one instead of doing a live one because turns out PinePhone Pro is not great as a video source. This part is OPT booting, and now we are into U-boot proper. Oh, sorry, one moment please. Here we go. Now U-boot is measuring everything and storing those measurements into fTPM. You can see interaction between OPT and U-boot as well as the underlying eMMC protected storage area. Now the Linux is booted up, and we should not be able to access measurement. Normally, T-Splicant will be able to figure out where is your measurement stored, but here I have to specify the ID because I'm running this off an SD card. Pardon?
When your head's turned, pointing.
Oh, I see. Here you can see the measurement stored in counter 127. Those are populated by U-boot. And then with fTPM ready to use, we can do things like emulate a FIDO token and then use that FIDO token to sign to different websites. Okay. I'm using server.debian.org, Debian's GitLab instance for my demo, but it also worked on things like Gmail and GitHub. There is no difference in setting this up and then compared to set up a real physical token. From the perspective of a website, this is the exact same thing. Now, if we log in, the browser would prompt us to authorize via the token. Yeah, here we go. Another application is that fTPM can expose itself as a general backend for store identities. For example, we can store things like SSH identities or OpenSSL private keys inside and delegate crypto operations to the security enclave. There is also no need to change application code interacting with it. The left side is connected to the console of the PinePhone Pro, and for things happening on Opti side, logged would be there, and the right side is the SSH console. Now we are initializing key storage. There would be two pings. One is a user ping, the one you use to unlock this identity. Another one is called SO ping, which is a concept from PKCS 11. It is used as sort of a recovery key. If you forget user key, you can still recover that identity by providing that recovery key. then we have to export the public key of the identity and transfer that public key to the remote server we want to authorize it into. Now it's possible to sign to server. Yeah, here we are in a remote server. All the encryption decryption process is done on the Opti side. Sorry, I have to rewind this a bit. Okay. Another method to increase overall security on mobile system I tried is using security by virtualization with Firecracker. If you use KubeOS, you will probably know what it's like to run workloads that way. But using full-scale things like Zhan or QEMU-backed KVM on a mobile system with much more computation and memory constraint is not very practical. However, there are lightweight hypervisors like Firecrackers, which would give you a more reasonable performance even on those low-powered devices, and while remaining same strong level of isolation. Typically, each workload starts in less than 3 seconds, and it has smaller attack surface compared to full-scale QEMU-based KVM emulation due to less emulated devices. For some of the use cases include disposable browsers. You can run less trusted websites in a browser confined by this container. Or you can also do things like convert risky email attachments like PDF within those disposable containers. And after operation, that container will be destroyed. And in reality, you can throw any workload you want into this kind of disposable containers as long as it's supported on Linux. So for my disposable browser, I have Chromium or Firefox that can be launched in this container, and the storage side is backed by a Btree file system snapshot. So each time you launch the VM, it's done with a fresh snapshot. So no information will be stored there unless you explicitly choose to. Optionally, you can connect this disposable browser to a disposable router, which route all your traffic through some kind of exit node to prevent traffic leak. However, there is still problems remaining, things like reduced performance and audio glitch due to the need to transfer audio from within the container to outside host system. And there is no hardware graphic acceleration, at least in this stage. It might be possible to implement that in future, but I think implement this kind of graphic acceleration safely is very difficult. And at the moment, host to guest interaction is very limited due to not having many emulated devices. This is the operating system booting within the container. Now it has booted, we can start our workload. I have to force Chrome to go through the VLAN composer because it's still default to X11. And here we go. This is all running on a PinePhone Pro. It's reasonably usable by PinePhone Pro standard. Yeah, you can scroll things just fine on the screen, and I think with newer revision of PinePhone Pro with higher performance, the overhead should eventually be unnoticeable. Some integrations, such as an on-screen keyboard, does work. So some further pathways include maybe we can take kernel measurements from Security Enclave itself. We can define a memory firewall policy to allow Security Enclave to access all the non-secure world memory, and then take kernel measurement from there. For example, we can monitor certain critical kernel structures to make sure that those are not altered during runtime. And if there is a security alarm, for example, if a critical part of the memory section becomes corrupted, Security Enclave might be able to shut down the system or at least issue a warning. Someone already tried that as part of the Shadow Box project, but I think that one is very much kernel dependent. You have to be running a very specific version of the kernel. Another use case might be use Security Enclave as an immutable storage for sensitive information like your log, so that in case of a total system compromise, the attacker will not be able to erase the log already generated, and this can be quite useful for offline audit. And we might also be able to run microkernels as VVM, as virtual machine monitors, and then run workload on top of that to achieve a greater degree of isolation. Gnode is already available for the original PinePhone, and I really recommend this talk. I think they've done a great job on this, and the end result is not completely daily drivable, but pretty close. And SEO4 can also be run on RKC 399. It's possible to run it on the PinePhone Pro, but with very limited functionalities. And if you have a PinePhone Pro, please take a look at my mobile project on GitHub. It provides a common infrastructure for building all those components and assemble them together. At the moment, it supports PinePhone Pro, but my aim is to eventually extend support to other open source Linux mobile phones, things like Librem 5. And it is designed to integrate with Mobian. At the moment, it contains a folder called Mobian recipes, which allows you to build full-scale Mobian images to work with this. But it is largely distro independent. You can throw any distributions you want. And since it's not for production, it's really more of a playground for new ideas in this space to evolve. And there are many things to be done. Hi, thanks everyone.
Thank you for your presentation. You mentioned storing SSH keys or TLS private keys in the secure enclave.
Yes.
Is there a PKCS 11 module to access this?
Right, let me repeat the question. The question is if there is a PKCS 11 module for accessing stored identities or keys stored inside Security Enclave. Yes, there is. There are actually two ways you can do that. One is through the native OPT interface. Another way is through the fTPM. Both are usable, and there are documentation for that.
Thank you.
Hey, you're talking about distros. So
Yeah.
what's in Mobian? So what's the status in Mobian? Like, have you upstreamed the patches? Can people install this or not?
Yes, you can certainly install it. The currently supported phones include PinePhone Pro and I think a few other phones based on Snapdragon. You can. Their website is currently done due to.
Sorry, not of Mobian. I mean of your work in Mobian. So if I've got Mobian running, can I just apt install or no?
No, because this all happens on the firmware level. You have to compile the firmware and then inject that into your image. And unfortunately, this is only supporting the PinePhone Pro right now.
Yeah, but I can update U-boot on my PinePhone, right? By installing a U-boot, and like I can flash the firmware. I guess the question is, what's the upstream status in Mobian? Like, are you planning to upstream this so people can use it and install it, or?
I think upstreaming this to be part of Mobian, this is on my long-term roadmap, but at the moment there are just too many pages to be first upstream to OPT first, and then it's a Mobian part. I think this is more on the long-term roadmap.
Any more questions?
I'm just curious, how much storage have we got on the OPT side for RSA keys and identity keys and all that stuff?
There are actually two ways you can store information. If you want storage, if you want to use OPT secure storage subsystem, one way you can store things on a regular Linux partition using and those things will still be encrypted. So if your Linux system compromised, those things will still remain safe because OPT will authenticate and encrypt those things. And on the hardware EM, say, replay protected memory block side, I'm not quite sure, but I think at least you have 128Ks, which is larger than most general tokens would provide on the hardware level.
Any more questions?
You had the demo of SSH and storing and creating keychains. How performant is the kind of round trip to the fTPM in terms of storing tokens? Like, is it essentially seamless to access those, or is there a delay measured in tens of milliseconds, or what does that look like?
I haven't actually done in terms of time delay. This sort of operation. I haven't actually done scientific measurements on that, but from my experience, there is no noticeable delay. The reason why there is a large delay with my demo is because I'm turning on debug information for all the file I/O operations, and this is very, very expensive. If I disable those, things should go much faster.
Was there another question at this table? So do we have any more questions? In that case, thank you very much for your talk, Yifei.
Yeah, thank you.